for the session here. So it's a pleasure to have everyone here today. My name is Shreyas Sundaram. I'm an associate professor here at Purdue in the School of Electrical and Computer Engineering. And today's event is hosted by the Center for Innovation and Control, Optimization and Networks, which is ICON. This is a brand new center here at Purdue that's bringing together controls faculty from across the College of Engineering and across Purdue. Anybody who's interested broadly in control of complex connected autonomous systems. The goal is to have an organization that brings people together. So this panel today is, one of the sort of the keystone launching events that we're going to be holding here to get the center off the ground. And the topic, obviously, is something that's of interest not only to academic community and researchers, but to the public at large, right? So the idea of robotic swarms has really captured the imagination of people from, observing the animal kingdom and insects to what we see in the movies. And so the idea of intelligent robotic swarms, the current state of the art, and a vision for where we're going to go with this and the capabilities that it's going to enable. We have 5 experts today that are going to be able to provide their perspectives. And so I'd like to just give a quick introduction to them here, and then I'll introduce them in more detail as they all present their perspectives. So we have Professor Spring Berman from Arizona State University, Dr. Erin Cherry from Northrop Grumman, Dr. Tim Chung from DARPA, Professor Shaoshuai Mou from Purdue, and Dr. Brian Sadler from the Army Research Lab. So each one of them will give about a 15-minute overview of their perspectives, and then after that we'll open up the floor for a discussion and questions. Okay, and so they're just ordered in by their last name, and so we'll go in that order as well. So I'll have Professor Spring Berman start off with her perspectives, and you can start sharing your screen, Spring. And as you're doing that, I'll just introduce Spring Berman here. So Professor Spring Berman is an associate professor of mechanical and aerospace engineering at Arizona State University. She directs the Autonomous Collective Systems Lab, and she's also an associate director of the Center for Human Artificial Intelligence and Robot Teaming, CHART. So this is something we were just talking about. Before joining ASU, she was a postdoc in computer science at Harvard, and she received a PhD in mechanical engineering and applied mechanics from the University of Pennsylvania. Her research interests include the design of control strategies for robotic swarms and other types of distributed systems. She's a recipient of the ONR Young Investigator Award and the DARPA Young Faculty Award. So Spring, I'll let you take the floor.
Okay, thank you. All right, so I'm going to talk about my group's research on control of robotic swarms with limited information, and then I'll have some points about what I see as technical challenges and future applications for robotic swarms. Okay, so my lab is the Autonomous Collective Systems Lab at Arizona State University. So we have a focus on, on distributed robotic systems. And so the 3 main areas of focus right now are, one, we look at scalable control of robotic swarms that have stochastic behaviors that can be operating in uncertain environments with limited information, possibly no GPS or local or no communication between robots. And so we look at ways to design control strategies that have theoretical guarantees on performance. Some of our strategies are biologically inspired by natural swarms, such as social insect colonies. We also work on decentralized control of soft modular robots, that is, robots comprised of soft deformable modules that have distributed sensing and actuation. And this is part of a larger project on building an octopus-inspired soft robotic arm. We're also looking at human-robot interactions, control, and teaming in the context of multi-robot systems. And so one application we've been focusing on is autonomous vehicles, replicating their capabilities at a miniature scale so that we can see how human remote drivers interact with autonomous vehicles and even study problems like ethical programming of AVs. So just some more details on some of these research areas that I talked about. So we've looked at strategies for task allocation and spatial coverage by robotic swarms that, again, have those constraints I mentioned. And so here's an illustration of some of the problems we've worked on. So a lot of our strategies use what are called mean field model abstractions of the swarm, representing it as a continuum governed by a set of differential equations. And so that's advantageous because you can apply analysis and control techniques to these models, and you just have to design a small set of parameters that can be programmed onto the swarm. And then the rest of their activities are autonomous and based on local sensing and information. So we've looked at problems like redistributing a set of robots among a group of tasks or locations just based on their local measurements, that ensuring that they get to a target distribution. We've looked at stochastic redistribution of a swarm by a leader agent that repels the swarm like a sheep herding dog. So you have even more minimal control inputs there. The robots just have to detect the leader. We've also looked at problems like swarm redistribution according to a locally measured scalar field, and also redistribution of robots that have nonlinear dynamics. So these are sort of density control problems that really lend themselves to a mean field model, multi-level modeling framework. And we have a survey paper about such models and their application to swarms in bioinspiration and biomimicry. Okay. We also look at problems of exploration and mapping, and we've applied different types of tools for this. So again, the robots are assumed to have local sensing, possibly local communication with each other. So we've applied techniques from topological data analysis to post-process noisy position data from robots that are randomly exploring a space with obstacles so that we can get topological maps or even metric maps if we have additional data, like a scalar signal measurement. We've also looked at ways that we can compute maps just using robot encounter times with features, distributed mapping using consensus approaches, so online mapping using local communication between robots, and looking at navigation problems where the robot doesn't know anything about the environment, but we can still use potential field-based approaches, local sensing, to ensure that the robot goes to some destination. Okay, so the last part of our research I'll describe is on cooperative manipulation. So in these problems, the robots have to cooperatively transport a payload using decentralized controllers, again, really limited information, no communication with each other, don't know about the environment beforehand. Some of these strategies are inspired by ants and were done in collaboration with social insect researchers. Others use other types of controllers that only require robots to measure their own velocity and to know properties of their own motion. They don't have to know anything about the other robots. So these are the sorts of problems that we work on. So now I'll talk a little bit about current and potential applications that I see robotic swarms being really useful for. So here are some categories of applications that seem to lend themselves to using robotic swarms. So a big issue right now is sustaining the natural environment by doing environmental monitoring and cleanup and conservation and restoration. So there's already been some work in that area. Maintaining the built environment, by which I mean inspecting, monitoring, repairing infrastructure. I know there's a lot of robots being developed for those purposes, like mine inspection by the quad rotors with Exxon Technologies, for example. Disaster response, another huge potential application. So for instance, humanitarian assistance, supply delivery, firefighting, search and rescue, like problems that Robin Murphy has worked on. I'm currently on a project which is on humanitarian assistance and disaster response applications by deploying a swarm of drones that carry food or water to stranded people. So those are a whole category of applications that I think could use robotic swarms. Also, of course, discovery, like exploration, mapping, underwater, in space, collecting samples where humans can't go. Protecting health and well-being as well. Given the pandemic crisis, there's been a lot more reliance on robots in some specific areas, like disinfection of public spaces and hospitals, as well as mobile food delivery with like Starship Robotics. So there might be some more coordinated applications or applications that coordinate multiple robots rather than single robots doing tasks in parallel. And of course, let me know if I'm getting too close to my time. Okay, so some other applications. So resource production and collection, so this includes agriculture, mining, possibly generating renewable energy even. Resource distribution, including logistics, so warehouse operations like at the Amazon Robotics, automated warehouses, transport, delivery of goods, manufacturing, construction, personal transportation, like autonomous vehicles. And there's been ongoing work on applications at the micro and nano scale, like nanorobots for targeted medicine, imaging, even surgery, and micro manufacturing. So, so these I see as the broad categories of possible applications for robotic swarms. And this is just some more details given that we're in the middle of a pandemic. So some areas where robots have been used are in mobile delivery of food on campus at, and around the area of ASU. So I don't think these could be considered really a swarm. They're not really coordinating, but potentially they could. And so you can imagine them delivering other items like supplies, medical samples for testing, sanitation, again, like I mentioned, disinfection, the UV disinfecting robots that are used in hospitals, waste disposal, trash collection that could expose humans to infection. Assisting medical personnel is another application for robots, and sending messages, signals to the public, monitoring compliance with quarantine. These are also discussed in a recent Science Robotics article by a number of very well-known roboticists. So, and then I think I'll conclude with some points on what are outstanding technical challenges for robotic swarms. So a lot of the work has been done in laboratories or in structured environments. And so there's a need to test in more realistic environments that may not have access to GPS, or you can't bring along an OptiTrack or Vicon camera system with you, where there's limited communication range dropouts. But I think, but Tim probably can talk a lot more about this in the context of the offset program. So, so I think there's also the issue with having robots that are capable of long-term or long-duration autonomy. And I saw an interesting talk by Magnus Egerstedt about robot ecology, sloth-inspired robots, where the robots don't do very much, but every so often they do something and they can conserve power that way. So we have to think about problems like that, where the robots are deployed for weeks or months at a time. How do we make sure that they're still operating, that they can that they can operate robustly in the event of failures or even hacking or adversarial inputs. And of course, the environment may be changing. There's random events happening. How does the swarm respond to those types of unknowns? So, and then we can consider the fact that so many robotic platforms have been developed for aerial, terrestrial, amphibious, underwater environments. So how do we coordinate them? And how do we create more complicated swarm behaviors than the single types of behaviors like flocking or consensus that have been studied very extensively? A couple of other classes of challenges: human swarm interaction. So how does a person control or supervise a swarm? What's the modality that they use? How do you avoid overloading them cognitively? How do you train a person to interact with them if they're not an expert in robotics? What kind of interface do you use? How do you build shared situational awareness and trust? Trust is a big thing. How do we foster appropriate trust of the person in the swarm? And then finally, I think I touched on experimental limitations, so in real world context, there's need to test out in the field, and there are a number of researchers doing that already. There are logistical challenges in making sure that you have the supply chain for your swarm or constructing your swarm is intact and robust. And how do you deliver? How do you get different types of platforms to different locations? How do you launch a swarm simultaneously? So these are a lot of challenges. There have been shared infrastructure like the Robotarium test bed, but there could be even potentially more collaboration among labs to take advantage of each other's strengths and facilities. So that concludes my talk, and thanks for having me talk here. And these are my students, past and present, who have done a lot of the work that I showed. So
wonderful. Thanks so much, Spring. That was amazing. So what we'll do is we'll save sort of interactive questions until the end of the panel when we do our main discussion. So for now, Erin, if you wouldn't mind setting up your talk. And for the audience, if you have any questions that you'd like to type into the chat as we're going, that way, in case there are pauses, we can answer those questions as we go. Perfect, great. So it's a pleasure to introduce Dr. Erin Cherry as our next speaker. Erin is a program manager in emerging capabilities development within the Advanced Intelligent Systems Organization at Northrop Grumman. She leads a portfolio of programs focused on swarming with attritable platforms, human-machine teaming, adaptive command and control. Erin joined Northrop Grumman in 2014 and previously supported a user experience team. She has a doctoral degree in information systems focused on human-computer interaction from the University of North Carolina at Charlotte. Erin, the floor is yours.
Yes, sounds good. Can you hear me?
Yes.
All right, great. Thank you for the introduction. So yes, I've been at Northrop Grumman for about 7 years now, and I'm a program manager. The projects I have today are focused on swarming and AI, and my personal interests really lie in that realm of human AI interaction. But of course, everything I'm doing is really enabled by a really great team, both Northrop Grumman employees and small companies, and definitely the universities that we partner with. So I'm really excited to be part of this panel to have the opportunity to engage with the academic community, because I'm really genuinely always looking for new collaborators. That's really important to me. So moving on to slide 2. On the left-hand side are images from the DARPA offset program, and Dr. Chung will deep dive on these in his talk when we pass it over. Our team does have tremendous experience now fielding those physical swarms. So the logistics piece that Spring was alluding to earlier, we're living and breathing that. In our last experiment at Joint Base Lewis McChord, we had to transport, deploy, and set up over 100 UXVs. So it was both the air and the ground. In our largest run, we had over 90 vehicles to one operator, but the reality is that there was a field team behind that to set up the vehicles at those launch points. And it is a large logistics undertaking. And then the additional experience that we've really got in building these physical swarms is also looking at how far I can get with simulation. And when I move into that testing for field experiments, for instance, how large does that subswarm actually need to be for iterative testing? If you're testing, in groups of 3, you might not see that behavior, but if you've got 30 out there, it might actually be too many platforms to actually pick up the subtle problems. So there's this delicate balancing act and really like how large you need for sufficient subswarm testing. And then, of course, that leads to the maintenance and consistency of the swarm, not just from a supply chain perspective, but from a software perspective, to having bits and pieces breaking on all of them. And, how consistent do you realistically need them to be? From a human swarm teaming perspective, I have many interests in this area, and I've highlighted just a couple of areas in the offset program. At the top here is our swarm engine software. That is for both simulation and command and control of both the real and the simulated vehicles. There's a YouTube video up right now, and you can kind of see this in action if you check out the YouTube video. And within Swarm Engine, the kind of interaction technique within that is these higher level commands that the swarm operator would draw as part of a sketch-based system. And then those higher level plans go through a bidding process, and the tasks are ultimately assigned to individual robots. That work with the sketch-based system was really a collaboration with the University of Central Florida. One of our developers is actually both a University of Central Florida student and also a Northrop Grumman employee. And below that is some additional work from UCF, which is focused on augmented reality. This tool is actually part of that larger swarm engine ecosystem. So the person that's wearing the headset, and honestly, that might even be Dr. Chung, but while wearing the headset, you're able to see the mission plan that has been sketched out. You can get a certain level of health and status information, and the representations of the UAVs that you see right here are actually real platforms that are flying. You just can't see them because they're above the picnic area. So moving over on the right-hand side, looking at Game Breaker, the Game Breaker program, while not specifically swarming right now, really drives implications for how you might optimize swarm compositions in the future. In this particular program, we're using a COTS video game called Command, made from a company in the UK. And within Command, we start with a balanced model or a balanced game. And we're looking at multi-objective optimization of platforms and effects, and looking for the combination that disrupts that model or the game the most, which is it's a really fun project. And then finally, moving down to the bottom for systems of swarms, we're starting to look at systems of many swarms. So then after you've optimized the swarm compositions that you need, then in this paradigm, you start looking at the different course of action generations and selections that are needed for a commander, and also looking at dynamic replanning. So this is kind of just a highlight of some of the projects that we're working on. And once again, they're all enabled by a great team. Okay, so to kind of highlight a couple of visions for the future, I'll focus here on human swarm teaming. I personally like to think of command and control as human command with machine control. And to look at it from an offset perspective of how we think of these human roles, we think of the command as making decisions to manage the battlefield, and the command post operator, who might be at that picnic table in the image before, we think of them as having primary control over the majority of the swarm, and they might be controlling it more like that platoon or the company level. And then finally, the role that we've started to introduce is the forward operator, They might be doing more precision tasking because, they have better, they're closer to the platforms and can see, so they might be doing more precision tasking, or they actually might even be tasked as part of the swarm. And that's an area that I really would like to be able to take this research and putting humans actually as part of the swarm in that multi-agent system. Of course, this brings a lot of organizational challenges to consider. So, at what level of command is the swarm controlled? Even just this depiction trying to show that there's many different layers of command, but, arguably it really could afford more decision-making at that lower rank, especially having access to all these platforms. And then I think another kind of organizational challenge to think about is, how much control of the swarm is actually needed. I think it's more in line with those higher level commands than necessarily like specific GPS coordinates that you have to go to. And even more importantly, the types of and amount of information that a swarm operator might need. You might not need, we as engineers need the debugging health and status of an individual platform, but as an operator, the information might be more of the health of the swarm as a whole. So I think that's a really interesting direction that one could take human swarm teaming next. And then I have one more that I've picked to look at, and I'm not really looking at, this is starting to be a new area. So a lot of people are starting to think of swarms as these attritable platforms that, they're expended, they can be mixed and matched. And, that mixing and matching, that mix would be, different types of platforms. So quads, fixed wings, loitering munitions, maybe even connected to, a network of larger platforms. And also have the mixing and matching of different sensors. So each platform would have a different type of sensor, for instance. And in that amalgamation of a new, basically each swarm then becomes a new system. So that swarm is novel and fleeting. It's not something that's been architected for half a decade or more. And because of that, when we start thinking about taking that, swarm amalgamation, it certainly brings new AI challenges for this fleeting system. There's no human training and bias to exploit for AI because there's no human that is, an expert in that new fleeting system. And because of that, there's no playbook to use, there's no playbook to counter. So I think this brings, a lot of implications, both at that planning level of what is the right composition to be the most effective, as well as the execution level. So those are the only two challenges and visions that I really prepared. But I also wanted to kind of go back to Spring's point about the GPS denied environments, no a priori data, and those are certainly challenges that we're living with today. And so we very much identify with them. That's it for me.
Awesome. Thank you so much, Erin. That was fantastic. Tim, you're up next.
All right, stand by. All right, can you see my screen?
Looks great. Yeah.
All right.
Thank you.
Cool, thanks. Well, good afternoon and thank you everybody. It's a pleasure to be here and connect with you virtually. And yeah, I was saying earlier that this is a fantastic opportunity to get a conversation going about some of these types of new technologies. As Erin mentioned, there's a program at DARPA for which I'm the program manager called Offset. And I see this program as been an exciting adventure, what I call a discovery program, because there's a whole lot of things that we don't yet know about swarms. And this program is designed to help us elicit some of those insights into what makes a swarm, as well as what kind of platforms or capabilities we still have yet to discover for those technologies. Just by way of introduction, I'm in the Tactical Technology Office at DARPA, for those of you who aren't familiar. And the Tactical Technology Office, TTO, is an office that prides itself on systems technologies, platform technologies. And that's why I find it to be a great home for me as a roboticist, because we pride ourselves in not only understanding component disciplines, but bringing all those technologies together into holistic systems. And I really like Erin's point about how a swarm is a system in and of itself. So, glad to share that with you today. So just kind of popping up a level to think about what it means in our case when we're talking about it here at DARPA. We like to think about.
I'm sorry to interrupt there.
Yeah,
we're seeing the presenter view.
How about that?
That's perfect.
All right, great.
And I apologize. I neglected your introduction, which I will do after your.
not a problem at all. And so one of the things that we find ourselves talking about when we're talking about swarms is, what makes it so multifaceted that it's so hard to talk about or really wrap our heads around. And part of it stems from maybe early definitions of swarms being, focused primarily on large numbers of low complexity agents. But when you take a look at it wholesale, there are many different facets here that lead to the complexity of understanding what comprises a swarm system. And so from this swarm pentagon, if you will, in addition to dealing with different swarm sizes based on their number and different types of agent complexity, meaning the types of capabilities they individually might possess, whether physical or software. But there's this other aspect of collective complexity, understanding how there's interactions, who's talking with whom, are there kind of leader-follower relationships, are there different ways in which the networking is dynamic or not. All of these things relate to the collective complexity attribute of these types of swarms. Another angle that was already previously mentioned by both of our panel speakers who went before me are the attributes of heterogeneity. Now, the exciting thing about heterogeneity is it's not just the platform or the payload that might be different, but you could have exactly identical systems, but you use them differently. So functionally, you have heterogeneity, and capitalizing on that in the context of these swarms is incredibly robust, and I think it's quite frankly a rich research area. And then the human swarm interaction piece, I think, is going to continue to be a key research area. This is where understanding what it means to do that interaction, not just one directional from the human or sets of humans to your swarm system, but also understanding what it means to present or convey information and interact the swarm back to the human. I like to liken this to instead of having, how do you imagine an orchestra, a symphony conductor? How do you have that orchestra conductor not have to tell each individual musician what note to play and when, but still find a way to get beautiful, harmonious music? Is there a way at some point in the future, from a human swarm interaction perspective, that it becomes, much more like improv jazz ensemble, where everyone's more or less riffing off of one another and still able to make that type of music? So this is one perspective that we at DARPA tend to think about. There might be different programs that we emphasize different attributes here, but this has really helped us start thinking about what angles we're approaching the problem. Along those lines, when we think about, again, enabling swarm capabilities, kind of outline these 5 pie wedges here. And I do think that it's the integration of all 5 of these tech areas that really will enable swarm capabilities, focused on the autonomy, of course, the human swarm teaming, but also the logistics, the swarm networking, and the swarm perception areas. I think we really need to build all of these up nearly simultaneously, if possible, to truly affect and realize swarm capabilities. So Offset is specifically focused on 2 of these 5 areas, and the exciting part here is that they're equal players. There's a co-evolution, co-design that's necessary between the swarm autonomy and the high, rich levels of autonomy we imagine these swarms being capable of, as well as how we go about teaming with them. So getting into the weeds a little bit more is what Offset is all about. we're really interested in developing the types of technologies that will enable large-scale teams of air and ground robots. We say that's in support of small unit forces, so that we have just a handful of personnel that are largely responsible for these large-scale teams, and they must operate in complex urban environments. And a way in which we're focused in doing that, envisioning upwards of 250 air and ground robots flying and driving around a city environment, is that underlying swarm systems architecture. And so, as Erin mentioned, we have these air and ground robot platforms. We're deploying them in large numbers. How do we go about doing that in the real world, while also enabling rapid tech development in a simulated context as well? So this underlying architecture allows for the kind of rapid turnaround cycles of playing things out in simulation, turning it into the real world, and then going back and forth and being able to iterate. One of the main tenets of offset is to, as Spring mentioned, try to elevate a lot of the research outside of laboratory or otherwise controlled environments. And so our approach in the offset program has really been zeroing in on this urban mission sets. So nominally in the context of urban operations, one can kind of structure a mission to isolate an urban objective. Really is, how do you go and surveil an area or identify where the fire is, or how do you respond to a particular emergency? That might require this isolation of an urban objective. We then move to what's called conducting an urban raid, but this is really about how do you go from outside to inside? How do you, again, put out that fire that's on the 20th floor of a skyscraper? That does require coordination from outside and from inside. And ultimately getting to this notion of an objective capability of seizing key urban terrain. And this is in the context of that, again, fire scenario. How do you protect that area, especially if you have structural integrity issues or spectators or other folks that need to be protected in the area, evacuation, et cetera? How do you manage a larger area over a longer period of time and be able to do that? And so the idea here is, at every turn throughout the phases of this program, we're interested in solving these kind of building blocks of urban mission sets. But as you can imagine, even something as constructing a perimeter and ensuring that you have communications connectivity, that's just one small nugget of being able to isolate an urban objective. And so these urban mission sets give us a rich opportunity, and I'd say even a lot of complexity, that encourage us to think about how to design our swarm systems in a way that is resilient and robust enough to handle these complex, typically adapting scenarios. And so to highlight that, right now we've just concluded one of our field experiments that Erin alluded to. This was out in Washington State, really focused on this 1 to 2 hour mission set, looking at about 100 platforms-ish, being able to kind of be deployed and then move off into the kind of city environment. And so this is just a highlight reel, if you will. Take a moment or two to highlight. We're, of course, sped up here, but you can see how, at least in this initial setup, we've deployed robots, ground and air, to respective deployment areas. Here's taking off. I think we've sped it up, I think 4x. And a deployment of units coming from a deployment zone, moving into the city area, trying to go and look for things, objects of interests, spot danger spots, etc. And there's a whole slew of things that have to happen under the hood here. Everything from communications to, as Erin mentioned, the field team, to having the batteries charged, to software configuration be deployed correctly. There's a lot that's going on, and all of this is so that there's a swarm commander, whether equipped with augmented reality or sketch interface or virtual reality interface or whatnot, being able to interact with these agents as they move through the space. In this example, you have some of these drones looking at buildings to see where windows and doors might be. Here's a deployment of roads heading down for them a highway, I guess, but basically a roadway as they deploy and expand and maintain communications, etc. So these are just some of the examples of what it means to go to a field, set up these types of large-scale tests. I think the experimental limitations are pretty severe, and one that I hope we as a community are able to find innovative ways to overcome. And so finally, I think among many difficult problems and challenges that have already been mentioned and will be mentioned, there are just so many that, you know, if you're a robotic swarm researcher, I suspect we have some good job security. But I'll highlight two that have been alluded to. I think the first is that swarm logistics piece. And I mentioned that here you're seeing a time-lapse video of a deployment of a team of drones kind of being pre-staged. And this is all happening in a half an hour, but you can imagine that we would want large-scale teams to be deployed much more expediently. And so everything from how do you transport, how do you charge, how do you fix and repair, let alone have a team of people go out and support this as well. So, DARPA Offset isn't interested in technologies that will accelerate that piece a bit as well. And then there's the other attribute here of, these robots in and of themselves, there's something to be discovered here about what makes for robots that work well in urban environments. So this is heading on to what Spring mentioned about, for example, GPS denied or otherwise inaccessible areas. There's something about these really complex environments that warrant a good look about the platform design, the sensing requirements, and of course the networking, and being able to say, here's a minimum capability of what we want to use to build upon. And I think we're still learning to some degree what that is. And so I think understanding both, the agent complexity, how it all ties together through technologies for logistics, networking, and perception, I think are still open and exciting areas for continued research. And with that, looking forward to the following conversations. Thanks.
Thanks very much, Tim. There was a quick question in the chat pertaining to whether DARPA has explored voice-based commands to deploy and move swarms from an operator standpoint.
Yeah, happy to take that. Yeah, absolutely. So we had very early on some investigations into how to do voice interaction. Siri and Alexa, all our friends can maybe help us along. I think there's still maybe a role to be able to do that, but it really depends on what we call the swarm persona, where that human action is occurring. If it's that forward operator that Erin mentioned, well then likely she's going to be in the midst of drones and rovers buzzing and driving around, lots of noise going on. Using voice might not be the right way to go, but if you're a swarm commander or a mission commander in a more protected location, then voice might surely be a rich way to interact with these swarms as well. Thanks for the question.
Thanks. Since I neglected to introduce Dr. Chung, I will do that now. Dr. Chung, obviously, thank you for the excellent presentation. He joined DARPA's Tactical Technology Office as a program manager in 2016. He serves as a program manager for the Offset program, as you saw, and also for the Subterranean Challenge. And if you go to their website, it's a pretty awesome looking website with lots of good information there. So his interests include autonomous unmanned air vehicles, collaborative autonomy, distributed perception, decision-making. Before joining DARPA, he was at the Naval Postgraduate School, and he was the director of the Advanced Robotic Systems Engineering Lab. He holds a Bachelor of Science in Mechanical and Aerospace Engineering from Cornell and a PhD from Caltech. So thanks again, Tim. Professor Shaoshuai Mou, you're up next.
Okay, sure.
So I will introduce Shaoshuai here. So Professor Shaoshuai Mou is an assistant professor here in the School of Electrical and Aeronautics and Astronautics at Purdue, where he directs the Autonomous Intelligent Multi-Agent Systems Lab, and he's also a co-director of ICON. Before joining Purdue, he received a PhD in electrical engineering at Yale in 2014, and then he was a postdoc at MIT for a year after that. His research interests include multi-agent autonomy and learning, distributed algorithms for control and optimization, human-machine teaming, resilience and cybersecurity, and experimental research involving autonomous air and ground vehicles. So Shaoshuai, I'll let you have the floor.
Great, thank you, Shreyas, and good afternoon, everyone. This is Shaoshuai. So today I will share my perspectives on intelligent robotic swarms. First is why intelligent robotic swarms. So by a large number of autonomous robots working as a cohesive whole could achieve swarm intelligence and solve specific tasks well beyond the individual agent. And if we look at the features of robotic swarm, at the individual level, and each robot is usually mobile, autonomous, and it's with low cost. But if we look at the whole swarm level, and Tim had mentioned, actually it will be large scale and also will be a heterogeneity there. And actually, since it's a large scale of autonomous swarms, and there are typically communication constraints to the information flow across the whole swarm. And also it's not practical to involve any centralized controller. And this gives rise to the core technique for swarming to be distributed algorithm for control, optimization, and coordination in the large swarm. By distributed, we mean that the algorithm could achieve global objectives through only local coordination. And actually, distributed algorithm have been studied for a long time. But if we look at future challenges, and here is a picture downloaded from online for a vision of future battlefield. From this, you can see that in future battlefield, there will be robotic swarms and multiple autonomous vehicles and air and ground vehicles working together. And there will also be human soldiers, which can give some expert input. And also the environment is usually complex and with potential adversaries. So from this, so future techniques need to address, I would say mainly three parts of the challenges for intelligent, robotic, and swarm. And first, because the environment is becoming more complex, which will involve a lot of uncertainties and high dynamics and with the potential adversaries. So we need the system, the swarm, to be intelligent enough to address all this uncertainty, dynamics, and adversaries from the environment. And also when it comes to sophisticated scenarios, human experts' input are usually necessary. More like we need to balance between autonomy, how much autonomy, and how much human guidance in robotic swarms. But we never involve human input. And usually the human input are sparse in terms that human can only give a few viewpoints, for example, and also it's not that accurate. Or I would say that usually it's hard to use analytical functions to describe the human's input. And also when it comes to swarming, and underlying swarming is usually a connected system or a large number of subsystems connecting together, especially under, for example, the network underlying the swarms will be a time-varying topology. And also each robot is usually with limited global information or can only access local information. So all the challenges actually arising from intelligent robotic swarms and require the integration of control, optimization, and networks, and also recent advances in AI and machine learning. So by noticing such integration, so that's why we have formed this new Center for Innovation, Control, Optimization, Networks. And the mission of ICON is to integrate classical theories in control, optimization, and networks with recent advances in AI, machine learning, and big data to address fundamental challenges in robotic swarms, or what we call is autonomous and connected systems. So currently we have 44 faculty members from more than 8 departments across Purdue. And also here the chart for the expertise of faculties at ICON will cover both classical theories in control optimization networks and also recent advances in AI, machine learning, and big data, and also human in the loop. So in the following, I will more like share my perspectives on future challenges for intelligent robotic swarms, and also Purdue ICON faculty's capabilities in this area, and also some of recent research from my group. So first, I want to say, distributed optimization and learning is a key enabler for the whole robotic swarm to work as a cohesive whole, or the optimal and adaptive cohesive whole. And here is more like a general problem formulation for multi-agent optimization, which involves 3 parts: a global objectives, which is assumed to be a symbol, and also each robot has some local constraints, for example, on their speed, acceleration, and also the goal is to reach a consensus. And this problem formulation actually has a lot of applications, like for a bunch of trucks, platooning, or the drone swarming, and also the, how the swarming of the robotic swarm interact with the environment. And for some future challenges, to name a few, for example, when it comes to multi-agent reinforcement learning, how should we decompose the reward function between the swarm and the environment into some local reward function? And also, there are already been many existing distributed learning algorithms, but there actually lacks a unified framework for analysis and design of digital optimization and learning algorithm. And at ICON, we have many faculties, including Aldo and Shreyas, Zhanghai, and Dengfeng, Martin, Philip, and all in this area. They have done many interesting work. And the second I want to show is that actually when it comes to swarms, and especially in future's complex environment, we were not assumed the environment to be ideal. So we will achieve not only autonomy, but resilient autonomy for robotic swarms. By resilient, we mean that the ability to prepare, plan for, observe, and recover from, and more successfully adapt to adverse event. For example, this is a 3 robot formation. If one of the robots is controlled by a cyber attacker, it can actually crush down the whole swarm. Another example is for a multi-robot rendezvous, and a bunch of robots want to gather at the same location. But under classical consensus algorithm, it can be easily achieved. But if one of the robots is controlled by the cyber attacker, and this robot could mislead the whole swarm. This is to achieve resilient autonomy for a robotic swarm is very challenging. And the challenges mainly come from the agents are the fact that agents usually are low cost with limited sensing processing capability and only have local information available, while the cyber attacks could be highly mobile, sophisticated, and could be launched massively from multiple locations. So this has given rise to the requirement of resilient autonomy in robotic swarms need to be automated, adaptive, and also works in a fully distributed scenario. And in this area, Shreyas, INSOC, and SM all have done networks towards resilient autonomy. And the following slide, I want to show 2 results from my group. And one is a multi-agent formation control. We more like integrate actor-critic multi-agent learning into distributed formation control. On the left-hand side is a control without integration of learning. On the right-hand side is the learning-based distributed formation control. You can see that without no attacks, both sets of swarm could form the letter P. But on the right-hand side, the learning-based control is a little bit slower when there's no attack. That's because we introduce this actor-critic learning. But when there are attacks, the classical distributed control usually not work, and they cannot convert to form a shape P. But on the left-hand side, learning-based one still works. And also, second one is more we have done some research on to achieve resilience for distributed consensus. We have considered time-varying networks, Byzantine attacks, and with time-varying locations, and also only local information available. And for more details, please refer to this paper. And next, I want to talk about more like, I would say, integration between control and learning. So there will be a classical series in control optimization and the network. There's also AI, learning, and big data. So usually, many researchers have successfully employed AI and learning and to deal with the challenges in control systems, to deal with their unknown, model-free, and also dynamics in environment, and also develop some data-driven techniques. But the question when we ask, when there's no data available for training, but we only have a little bit of control structure, how should we do in this case? Or how should we use control concept to help the development of machine learning? And we also have a bunch of faculties and in this area. And here is more I want to share with you our most recent research, and which just accepted by NIPS. And we more like to utilize simple control concept to develop a end-to-end learning framework. And here is more like a general control learning problem. We have optimal system, which can be a robotic swarm or unmanned vehicles, and with a tunable parameter theta. And we also have a loss function, which can evaluate whether the system is under good performance and based on its a trajectory, like X and a U. Or you could look at this loss to be like new constraints for obstacle avoidance or safety or resilience requirement. So the problem is to minimize the loss and only based on the output or the state of the optimal system. And the challenge here is that actually d xi over d theta is usually unknown. But of course here you may think, oh, let's use a neural net to approximate the relation between theta and xi. Yes, we could do that, but that requires pre-data for training. So we more utilize a little bit about utilize a feedback concept and also optimal control. We more like introduce another auxiliary control system in the feedback loop from the trajectory data to the tunable parameter theta. And we'll achieve an end-to-end learning framework. And actually, we can solve many control and learning tasks. And first, I want to talk about human-autonomy interaction. For example, there have been a very hot area called imitation learning, and human experts give some demonstrations, and the robot could learn from these demonstrations. Or when it comes to sophisticated scenarios, human experts' input are usually necessary, for example, for path planning in an environment with a lot of obstacles. The challenges involving human input is that human input are usually sparse. It's only a few waypoints, and also the human input are usually weak, and usually it's hard to get an analytical equation to describe the human input. And we also have several faculties working on this area and ICOM. Here I want to show you our most recent research, which submitted to more on the UAV, how to teach a UAV to avoid obstacles by human sparse inputs. The key idea here then we integrate human sparse input into robot's object learning. If the robot is driven under optimal control. And here you'll see actually a drone, if only one waypoint available, and the drone could performance is okay. But if 2 waypoint available, the drone could pass through these 2 doors smoothly. Or 5 waypoint available, for example, if human want to produce a desired trajectory. And fifth, we also, at Purdue, we have the simulation platforms, especially designed for intelligent robotic swarms. This is called Swarm Simulation Portal. This is under development by a team of Purdue undergraduate students led by Professor Shreyas Sundaram. And this is special designed for simulation robotic swarms. It's a cloud-based platforms with some swarm library, and also it supports MATLAB, Python, and C++. Here is a video to show this. You can say the environment is more real than disabled, for example. And of course, besides simulation at Purdue, we also have the strengths for implementation and integration for intelligent robots. We have individual labs for my lab and Professor George's lab, and especially Dave Cavalari's lab is for multi-scale robots and automation lab, and also Song Zhang's lab for 3D sensing. And especially this semester, Purdue had launched a large US test facility at Purdue Airport, which can host a very large robotic swarms. And also for integration, we have Center for Innovation in Control Optimization Networks. We also have Purdue Engineer Initiative with special focus on autonomous client systems, and also robotics accelerator, and also IGSDI for applications in defense. And to conclude, I want to say our future vision for intelligent robotics swarms is that plus AI and a human in complex environment. And this is one ongoing project which I'm leading now. And we aim to develop an AI system multi-agent platform to provide distributed environment perception, situation awareness, and perform real-time dynamic distributed control and management, and also involve human in the loop, and also improve performance as the time evolves with help of learning and AI. I want to use this short video to conclude my presentation. This project is funded by Northrop Grumman. And also, thank you for your time. And if you have any questions, feel free to email me and also go to our account website for future events. Thank you.
Thanks a lot, Shaoshuai. There's a quick question in the chat about training the robots in your setting. Is the training done in a centralized way and then the learned policy is distributed, or is all the learning also done in a distributed way?
Oh, actually, that is a very good question. And so that is not that fully distributed. And after training, then it's running fully distributed. That's why actually that motivated us to say that, okay, we will not involve any training stage, and whether we could do it in an end-to-end learning fashion. That means there's no pre-training, no data available, and we just embed more like the feedback loop to achieve this kind of online training.
Great, and there's another very quick one, I think that's specific, so we'll just take it now. Are you using inverse reinforcement learning?
No, actually, especially for the how to integrate human input into the autonomy, and we did more like, okay, we will. The key idea is to integrate that into the object learning. That could be done typically through inverse optimal control or through the inverse reinforcement learning. And we more gonna move further from that, and especially in terms of existing techniques in inverse reinforcement learning, you will require a full demonstration of data, and also the techniques can only deal with like this single phase cost function. We could deal actually if multiple machines mixed together into a multi-phase cost function. We want to achieve a little bit more than ARL.
Thanks, Shaoshuai. Dr. Brian Sadler is up next. Perfect. It's a great pleasure to introduce Dr. Brian Sadler as our final panelist here. He's the Army Senior Scientist for Intelligent Systems at the Army Research Laboratory. He's a fellow of the ARL and IEEE, and he's an IEEE Distinguished Lecturer. He's made significant contributions to a wide variety of areas and is a key player in the space of intelligent systems. His research areas include, in addition to intelligent systems, AI, ML, multi-agent autonomy. He has more than 450 publications with over 16,000 citations. So he's made significant impacts, and it's a pleasure to have you take the floor, Dr. Sadler.
Shreyas, thank you. It's great to be with you guys today, and it's really nice panel. I don't know if going last is good or bad, but you know, it's interesting how highly correlated we are, number one, and number two, you know, I've been tracking this area now for 14 years, and the progress is remarkable and accelerating. So it's really interesting, exciting time, and I think setting up your, you know, your center at this time is quite timely. So I want to talk through some issues from a high level. You know, we have a lot of great projects going and internally and with collaborators and things, but I thought I'd just talk issues, and some of these have been touched on, some haven't. So, you know, some of these have been touched on, some haven't. So, You know, when we think about the Army problem and these operating in these difficult environments, we like these kind of cartoons of dense urban, you know, there are estimates by 2050, some rather large percentage of the world's population is in dense urban. It's not the only complex environment, but it's certainly representative of a lot of significant research challenges. And, you know, although somehow our cartoons influence the way we think about research questions, so it's kind of interesting. You know, but eventually we're talking about large numbers of agents, and the Army is clearly on a path, and I would say in two ways from a R&D perspective. One is we're moving more and more to systems. I see this across ARL. I see this across commercial industry too. We're doing more and more in systems. We get more technology convergence, and this area is very representative of that. And the other thing is more and more distributed, larger scale operations. And this is affecting us in the way we communicate, not just in robotics, but in all sorts of things. And I thought Spring's list of potential applications here is extremely exciting, and, you know, going to benefit society in many, many ways. I want to emphasize really talking about a heterogeneous mix. Right? We can have large ground vehicles, large air vehicles, small quadrotors, and etc., air and ground. The ground problem is so much more challenging than the air problem just because of the sheer obstacles, right? Let alone the indoor-outdoor piece. And autonomy takes on a whole different perspective when you're on the ground versus in the air. The air problem is so much easier that we're already seeing significant leaps in the air kind of behaviors, whereas the ground in general is going to lag. And so there's a lot of benefit to be had for ground operations when you also have air. And, you know, we see soldiers in various different roles. So obviously these are highly collaborative, highly distributed, might mean city blocks, it might mean kilometers, it might mean much larger scale. And so we think about things like injecting autonomy into a scene. How can I throw autonomy 100 kilometers from me and have it do some task? And the wireless networking piece is really critical, and I'll say a little more about that later. But, you know, in the commercial world, as 5G progresses, we're seeing things like UAVs being envisioned as part of that infrastructure. But the Army can't assume that we have infrastructure. So, and the same thing may apply to disaster response and so on, health crises. And so we have to be really careful about how we think about the networking piece. And the other thing for us is contested environments. We want to go fast, and we're going to have adversaries, you know, and a lot of times nature is an adversary, right? So it's not even necessarily an intelligent adversary, right? And clearly increasing in this space is more use of semantics. We're getting better perception and awareness. We're not where we need to be in terms of group perception and awareness, and adapting behaviors, not just setting out to do a particular behavior, but how do we do adaptation? So let me talk through a few things. One of the key things is how do we represent and share knowledge within a swarm or swarm to human and so on. There's at least two major threads here. One is we use something like a deep learner to do a compression abstraction of information. That usually means we put ourselves into some kind of abstract vector space, which is fantastic, and we can do so many things with that, and yet the vector itself is just a string of scalars to me, and I have no interpretation. Alternatively, I can have something like a semantic knowledge base or reason over semantics, which are inherently, we could say, interpretable or understandable to a human, but in a lot of ways more difficult to deal with, much more ad hoc. And how we go across these two spaces is a real challenge, I think. So I mentioned the wireless, and for the Army, wireless is fundamental and extremely challenging. So one way I encourage everyone to think about this is from a multi-radio perspective. Right now in your cell phone, there's something like 4 or 5 radios, which operate in different frequencies, i.e. different wavelengths, and they have different purposes, like cellular microwave for long haul into the infrastructure, Wi-Fi for short range, high bandwidth, Bluetooth for very short range, ad hoc, and so on. So we have to think the same way about the swarm problem. We have line of sight, we can use it. We could say use millimeter wave that's emerging in 5G. We can use optical and so on, but we won't always have line of sight, of course. We still want to use things like ad hoc, microwave. We're also looking at low frequency communications. And here I mean low VHF, like wavelengths on the order of 5, 10 meters, because they penetrate buildings and give us connectivity, although they may be low bandwidth. So there's a lot to this picture. And the more we think about how we incorporate that, not treating it as a separate thing that we're going to bolt onto robots, the better. Like, so for example, you can think about a swarm as providing networking backbone. Right? Or you could think about the swarm, in order for the swarm to operate, I may have to have elements of the swarm dedicated to the communications. Right? So these are really interesting mixed problems. And one of the things that we do in order to get traction analytically is we like things like distributed optimization problems, consensus problems, and so on. And I've worked in that space, and even with Aldo Scutari at Purdue, we published some stuff. And, you know, but a lot of this relies on this notion that we're going to gossip for a long time, many rounds of gossip, and things are slow to converge. And, you know, but if you step back and think about it, what you've done is you've pigeonholed yourself in terms of a form of communication. I want to talk to my neighbor. I want to talk to my neighbor. But I can flood the network. I can consider long and short range links. I can do power control. I have a whole suite of things that we've developed in the last 20 years in cognitive and adaptive networking, beamforming. We're looking at distributed beamforming with swarms. A lot of things we can do here, right? And we can fold them into the swarm thinking in a much more intelligent way, I claim, than we're doing now. It's hard. I'm not saying it's easy. And analytical traction is really hard. People have brought up the modularity and heterogeneity and, you know, dynamic teaming. And this is a huge problem for the Army. I think Erin mentioned the logistic tail, and those are all serious issues. As I like to say, there's no Moore's law for batteries. Right? We're really good at making better computers and more complex algorithms, but batteries are always kind of lagging behind. And so the notion of how we use energy is always folded into this, right? And, you know, whether it's energy conservation or energy harvesting or recharging dynamically, or, you know, with time scheduling within swarms so that some and so on, right? These are all still open problems that really demand our attention, especially in the ad hoc setting. I think another interesting theme is, you know, handling a large disturbance. So we think about resilience from a perspective of like communications or topology, reformation, right? But in those kind of resilient robustness things, we may be thinking about small perturbations. We've got a group, it's going to do something, it's communicating, it's searching, it's building up a map, and there's some perturbation, one agent dies or something like that. We have to think about large disturbances. Right? If we can tolerate really big things, you know, then I think that's another unexplored area. Pretty much everybody touched on the swarm and the human piece, and, you know, this is clearly just autonomy generally, whether it's a single agent and a human interaction. And there are many faces to this. And if I go back 10, 15 years, it used to be we had this sort of human robot interaction guys over here, and we had the roboticists over here, and they would occasionally talk. And, you know, the opportunities here to get us all together in a multidisciplinary way around these problems are really exciting. From a swarm perspective, it's useful to think of the swarm as a teammate. And, you know, I know, and I'm military side of things, you know, swarm, go do that. Well, that's okay. But you know, I like the idea of that the swarm is going to facilitate and help and interact. And how we do that is not obvious, right? How does a swarm represent information and pass that back to a human in a way that the human can use that, right? Because I don't want to burden the human any more than I have to. And Tim and Erin, I think, touched on this. You know, when a guy is out there doing a tough job, you really don't want to bother him. In fact, what you really want to do is, I've got some guys over in a particular situation and things are really going wrong for them. They're in serious peril. Right? I, as a remote guy, want to push autonomy to them. I'd like to task a swarm, go help those guys, provide situational awareness to them, provide communications to them, and do it in a way that you really don't bother them very much. You just help them, right? I don't want to be the troublesome little brother who comes along, right, and becomes a pain. I want this to come in, right, to be additive and relatively transparent to them and provide and seamlessly integrate into their services. So this is a way to think about, I think, but how we do this, how we do the querying, you know, I think that this is a really rich research space. So one last thing, you know, in autonomy generally, we don't have a good science of test and evaluation. As soon as we fold learning into the picture, we don't have a predictive theory and we don't have a good way to say that how we're going to do test and evaluation. The old style test and evaluation with the clipboard and the, you know, no. Right? So we all see this. But the multi-agent swarming aspect offers us some interesting opportunities, right? So I can imagine, well, I have an executive who's overseeing the swarm, but actually the swarm can oversee itself in the sense that I see you, you see me, you see Bill, Bill sees John. We can all kind of monitor each other, right? So oversight kind of takes on a sort of interesting avenue, especially when we're all communicating, we may be spread out. We might not have line of sight to all the other swarm members and so on. And then how does that fold into human oversight as well? It's not clear because, you know, why would I assume that a human has eyes on all the swarm at any given time? Or that the comms are so good that I know where everything is all the time. I don't want to assume that. I think that's a very unsafe assumption. You know, we like modularity and composability. We naturally progress to this. It's like constructing the internet, you know, or any other complex system. We want to do things in a modular way. I want to be able to drop in a new perception module and see how it works. And that should enable test and eval. Right? But if you think about it from a behavior standpoint, you know, we like behavior trees. They're really well founded in video games. They work great. But, and this is not I don't mean to be controversial. We've naturally progressed into behavior trees and playbooks and this kind of thinking. But is that sufficient and is it sufficient not only to achieve the kind of behaviors we want, but to react to adversaries, but also to enable test and evaluation? The richer I make the behavior space, maybe the bigger the challenge is in terms of test and evaluation. Right? The more I let the system kind of go off and do its own thing, the more difficult it is to test and eval, the more difficult it is to oversight it. And in fact, maybe even the more susceptible it may be to some adversary's interdiction, right? This is an analogy I'll use is dynamic spectrum access. We want to be able to sense and react and move and all these things. And yet, if an adversary can come in and just kind of jump in and out of your system in a seemingly random but designed way, it may well force you off into a regime you don't want to be in, right? So these questions are complicated, and I think the research space here is wide open. So the last thing I'll say is risk versus reward. So from a military perspective, I really like to have the tools, not just to have the swarm go off and do something for me, but I'd really like to have a risk reward knob. And so if I'm in a certain kind of operation where safety of life is critical, speed is not, I'm going to turn the risk all the way down. We'll go slow and it's fine. But there are other cases where the building's burning and people's lives are at stake. And I'm willing to commit extra agents to get into that building, like in Tim's scenario. And I need to get in there fast and search that building really fast. And I've got a lot of extra agents. I can commit to that task because it's a very high priority for me. And you know what? If some of them crash, okay, that's okay. That's a risk, right? But I need to characterize that risk and I need to give it to the commander, to the medical doctor in the field, whatever that situation is, right? I need to enable that person to have that resource in a way that they can adapt and use it for their particular application. So I'm going to end there, and I appreciate everyone's attention.
Wonderful. Well, thanks very much. That's, I know, I think there's virtual applause from all corners here. We'll open the floor for questions. There are a couple questions in the chat. Some of them were centered around certain themes, and so that were touched upon, and I think it might make sense then to delve into some of those themes. Certainly, communications was an issue that I think almost everybody raised as a challenge in the space. So Russ Shirey had asked a question. Russ, if you're here, I'll have you unmute and ask your question yourself.
Sure, yeah. Thanks, Shreyas. This is to Dr. Timothy Chung. Thanks, everybody, for the presentations, by the way. I was just curious what kind of communication network you're using for your swarm communication, and if it's like a omnidirectional ad hoc network, or just was looking for a little more information on that.
Yeah, sure. Happy to share. So we have two teams. They use two different approaches. One is actually using a private LTE. So now you're using a base station. All of the robots can carry their own LTE modems, and essentially does lend itself to a hub and spoke communication network, even though the cooperation topology is still it still looks very distributed agent to agent. It's just that the communication of data goes through the base station. And then our other team uses, in the Wi-Fi bands, mesh radios that are commercial off the shelf. And in that situation, there's meshing that happens at the proprietary levels, but in terms of information coordination and such, that's nominally all shared in that space. And then there's been explorations in a number of other arenas, but those are the two primary comms channels. Thanks.
Great, thank you.
So just to touch on that and expand, just because communications was identified as a key challenge, are there new paradigms that are going to need to come up in order to be able to enable swarms, especially with things like nearest neighbor communications as these things scale up? Is interference going to be a challenge? Hub and spoke, you mentioned, Tim, is that feasible? Brian, you'd mentioned sort of the ability to transmit some pieces of information long range, but that's not feasible, in short range, or it might cause too much interference. Are there new ways that we need to think about things, or is it mostly adapting existing technology and figuring out how to inject it into the swarm setting? And anybody can take that.
I think it's a little bit of both, because even if of course, we're going to adapt and pick up and use, and like we'll benefit strongly from 5G directional links. Right? I mean, there are now, little tiny arrays that can go on the side of your cell phone. These have been prototyped already. So certainly we're going to strap them on every quad rotor. But we also need to think, so what do we need to think about for behaviorally, right? If I move closer to you, then I get a physics advantage, and that'll help us close the link. If we maneuver to get line of sight, we can close the link even in an adversarial situation, because it's much more challenging to jam that line and so on, right? So the answer to your question is yes. Right, and we'll benefit from all the development in cellular miniaturization, but we also need to think about behaviors, right, a mix of behaviors, and I think we should also think from a heterogeneous perspective, because I can pack a lot of stuff in one vehicle. A military vehicle can carry a lot of computing, a lot of antennas, right? So if you think about it that way, I can bring along some significant centralized comms and computing, but we need to think this through, and I think that those are rich sort of systems perspectives to explore.
Did anybody else want to add anything to that? Or?
Yeah, I'll jump in. I think as Brian mentions, it's not just the fact that we'll have networking, it's how we use it. And I think it really dictates the context, or the scenario, or the mission really dictates the innovations that are still required to be had. And I think maybe kind of popping meta for a second, it's the ability to adapt and change. Just because I have a 5G radio doesn't necessarily mean that's what I need all the time. So maybe I just need to, rock my wings a little bit, and that indicates to a vision-enabled teammate that that's, that you got the cue. So is there a non-RF based communication? And that really changes. So I think much like there's so many design variables in swarms writ large, there's so many design variables on the communication side that's that has, I think, yet to be tapped to its full potential.
Yeah, I agree with that. This is Russell again, just from a, I guess, student side. I'm one of Shreyas' students, and we're doing a lot of experimentation and research on the side of network communications with unmanned aerial systems. And, Dr. Sadler had mentioned power, and things like that, because there's always that option, right? You can increase the power, you can add amplifiers and then extend your distance, or as discussed, you can switch to directional antennas, but then you have to formulate the flight path. Or we've done kind of fixed wing UAS experimentation where there's symmetry differences. So when the UAS is, at a certain angle, there might be, better or worser communication. So yeah, definitely an interesting aspect, lots of variables. So I definitely appreciate the conversation.
There was another question in the chat from Wei Shi. Wei, are you there? You could ask your question yourself if you'd like.
Yeah, I'm right here. I'm just wondering so the battery, the battery is always an issue, right? It can be running out of the very quickly. So what is the possibility just use the conventional fuels? And also add the capability, just refilling in air in an autonomous manner. That would greatly extend the range of the drones, for example.
So I think this goes to the long-term autonomy aspect, and Spring, I believe you'd maybe discuss some of that. I don't know if you have any thoughts on that.
So using fuel versus battery power.
Yep.
I guess would that work for a larger type of vehicle? Yeah, I guess it depends on the size. Yeah, so I'm not sure. Yeah, the batteries still have limitations, but I guess you'd have to compare like a large UAV with conventional fuel versus state-of-the-art battery in terms of cost and range. So those are just my thoughts on it.
Yeah, actually for the Shaoshuai and I think Professor Li Chao in our department and we had talked about this, whether how should we more like use the regular fields to replace battery in the small size of core rotors. But actually that's more like I would say the combustion and engine control, all this kind of problem. And actually I'm not aware of any small size of core rotors using fields. I would say I didn't see. I would say there's a possibility, if researchers from multiple areas could work together to develop maybe a commercial used drone, small drones, and for that. But I think, as Spring said, actually the size of the drone that matters. For smaller ones, it's difficult to use regular fields. But maybe it's possible in the future.
Mirko Kovac at Imperial College, I think he had a combustion propelled like very micro vehicle, but at least a few years ago. But yeah.
For air ones or the ground vehicle? For ground vehicle, I can see it might be possible, might be available.
Yeah, I'm not sure what he's done.
I think this might be a very good direction to improve the maximum flight time, for which is, I think, one of the major shortcomings for drones. And either we could get a better battery, or we change the traditional structure for them using the regular fields.
Okay, Amir had a question. Amir, are you there? Would you like to ask it yourself?
Yeah, thank you. Thanks everybody for nice presentations. My questions for Dr. Chung. let's suppose disaster situations when the map of buildings or the environment is not valid anymore. So, I mean, due to the structural change caused by a disaster. So how can we properly navigate the robots in these environments while guaranteeing accomplishment of the tasks?
Yeah, this is a great question for probably all of us. And there's some nuances to that question. So the fact that you can properly navigate in a changed or dynamic environment, well, that's something that we roboticists love to do, you know, whether it's map changes from a SLAM perspective or being able to adaptively navigate in changing environments, but it really dictates the type of sensing and perception capabilities, whether machine learned or otherwise. But you also made a comment here about guaranteeing accomplishment of tasks, and that guaranteeing, that means something very, very specific when we're talking about different types of missions. And so having some notion of assurance or formal proof that your agents will be able to get from point A to point B in the context of uncertainty, that's its own area of research, as you know, as well. Not quite sure that's where your question was going, but speaking to some of the things that Brian and others mentioned about trust and test and evaluation, that space of test and evaluation only increases exponentially when you have so many agents, and finding smart ways to be able to do that, I think is key. But maybe going to the surface of your question there, I do think that resilience in the face of uncertainty, whether that's spatial uncertainty or temporal in the sense of dynamics, temporal uncertainty, I think that's you know, that's what robotics is about, right? Trying to imbue that kind of autonomy in the face of that uncertainty. Valid question. Thank you.
Thank you.
Just to follow up on some of the themes that have been circulating there, Erin, you'd mentioned sort of this emergence of attritable platforms, right? Essentially low cost, things that might be, it's okay if you lose them. Presumably there are implications for attritable platforms in terms of their communication capabilities, et cetera. You may not be able to put expensive things on them. So would the perspective with an attritable platform then be that you send out a very dense set of agents in order to be able to compensate for lack of other things?
Are you speaking to, so from my perspective, one of the things that I hear when we're talking about attritable platforms is certainly keeping them down below like a certain cost, because by the time you start adding more, you know, platforms onto them, at what point, you know, like what's the threshold that you're okay with it being, you know, expended? And I think that question really comes back to like, you know, like, and I can't speak too much to it from like a conflict perspective, but it's basically, you know, that cost imposition is what is important. So I think that's what they look at when we're talking about, you know, compositions of attritables. But it is true that, you know, you might have and I think an active area of research is, it is true that within that like amalgamation of attritables, you can take down, you might be able to take pieces of it down because maybe it's part of it's very susceptible to damming or something like that. So I think there's a lot of interesting questions there as well.
Great, thank you. UA asks, are there any publicly available benchmark data sets for heterogeneous swarms? So if we wanted to, you know, play with heterogeneous swarms and design them, you know, what's a good way to start?
You know, we use simulation a lot for this kind of thing. I'm not aware of any publicly releasable, you know, we all fight the same problem. You think on the government side, we have a lot of data, and no. So this is a challenge because it costs you so much to get good data, right? And instrumenting a test of any kind of scale is really hard, as Tim would, you know, testify many times over, I'm sure. So.
And even when you're collecting that data at a test, I mean, it's data that you're collecting in the wild as well.
Yeah, and yeah, absolutely, we'll follow that up. I am this is one of those places where having something like this would be phenomenal, but finding consensus on what that benchmark data set would be is so incredibly hard. So I can speak for the offset program that there is an abundance of data, but it really depends on if you're looking at things like, let's say, telemetry, robot positions, and is that sufficient for the type of research that someone might want to make use of this data set. On the other hand, if you're talking about fleet preventative maintenance, and now you need IMU and other accelerometer data or hardware data or GPS sensor data or other things that are large scale data sets because you have large platforms and you want to study those trends, well, that's a whole other class of data sets that could be captured. And then of course, all of the sensor data, whether those are camera feeds, LiDAR scans, any of those kind of things are their own rich data sets. And so for offset, one of the things that we're keenly interested in doing is creating a data set about the mission or the scenario, so that at least if anyone wants to bring a swarm into the simulator and test it out, at least there's a common scenario or a common mission with nominal performance measures that people can benchmark themselves against, not necessarily the data arising from the swarm execution themselves. And then as Brian mentioned, it's really going to be clear that simulation plays a role, but simulation's cheap, and the data that arises from that is quote unquote cheap, but you can only trust it as far as you trust the simulation, and that's also equally hard. So I think a concerted effort to develop, whether it's government sponsored, like Brian mentioned, it's not easy to find these data, or if there's a community consensus on at least maybe a coalition of like-minded swarm data set collection enthusiasts, and then those get, honestly, if there's just a schema for what it means to be a swarm benchmark data set and folks can start generating data according to that schema, that would accelerate, I think, communal development for sure.
Sounds like a good task for, I'm sorry, Tim, I was going to say it sounds like a good task for Purdue.
Ah, there you go. Yeah, they walked right into that one for sure.
Well, we got plenty of students looking for things to do, right?
Right.
So.
Right. And Spring, I think you mentioned, the way to do that with common or communal data sets as well as remote laboratories. I think you have a lot of experience there as well.
Yeah, I think, no, it would be great to have like common data sets that could be used to compare controllers or compare different algorithms in simulation, or even in experiment, if it's possible. Yeah, I guess we'd have to, the robotics community would have to agree on what are the salient characteristics of such the scenario that's being, I guess, tested out. Like what are the main features, and in developing test beds within the chart center, like we're also facing these questions, like what type of lighting or sounds or media projections would be most useful. So that would be interesting to come to a consensus on like several, scenarios or use cases and what are the required features. So yeah, it's, but it would be nice to have a common basis of comparison for controllers and other algorithms.
Yeah, this is an incredibly fantastic opportunity to get to next level type of advances. I think building on communal reference sets will definitely be key, and it could be done in pieces, right? Like you said, the perception piece, swarm perception. It could be the swarm networking, and folks log RSSI between robots, and that's just the only data set that gets released, and everybody else can use that data set. There's a really rich opportunity there, and I think the community is pretty thirsty for such data.
Tyler Federizi, if you'd like to ask your question.
Yes, thank you, Professor. So thank you, everyone, all the panel. This question specifically for Dr. Sadler, something that you mentioned about utilizing playbooks, but it's open to everybody. So from the perspective like of an operationally using swarms in a support role, using a small team on the ground, they may be engaged in a dynamic environment, so a firefight, and they lose communications, and now they can't actually communicate back to command, so they need support. And so one of the things that you had mentioned was using a drone to kind of send people out, but that when you get to where you're going, if you can't communicate with a ground team, has there been any research or is there interest in what I'm going to call, and I might be using this wrong, but semantic support of trying to understand the environment, which is highly dynamic, and then being able to basically communicate back action plans and have those approved by the higher level commanders, and then kind of action on those plans in a way to keep in a way to provide support and still have oversight of the swarm, so the swarm's not running around doing crazy things, and then just kind of base that on maybe the rules of engagement or something like that.
Yeah, it's an interesting question. I mean, really the first piece of your question is, can I observe some operations and infer, right, or reason about? It's a perception problem. I'm trying to observe maybe my own guys and decide what it is they're doing or how they're operating. We have thought about, there's certainly, thinking about problems like that, especially when it comes to robot-soldier interaction, because you'd like the robot to look at the soldier and understand what the soldier's doing, right? And so like in a tactical situation, these guys are trained to behave in certain ways and not in other ways. And if a robot is rolling along with a squad and the squad takes cover, then the robot ought to be able to infer that, gee, I ought to get out of the middle of the road and go hide, right? So you could certainly think about building in those kind of behaviors. And we also think about how would a robot traverse from A to B and also, maintain radio connectivity or maintain some stealth or not be noisy or not be observable, right? So we start to think now about, inserting a desired, not just going from A to B, but inserting some desired characteristic with that. But I'd have to say that's probably as far as we've gone in that direction.
Did anybody else have any? Yeah, Tim, if you'd like to.
Yeah, I think if you look at the name of our program, Swarm-Enabled Tactics, what does that mean? Well, we think of tactics as the kind of translation from commander's intent, whatever she is trying to effect on an urban setting, in the offset's case. How do you translate that into something that's not like a waypoint controller and tell me what that pixel is telling you? It's at a much higher level, and so for the offset program, we call those swarm tactics, and we're interested in understanding what are those foundational requirements on autonomy, swarm autonomy, that will allow for the swarm or the subswarms to execute those high-level swarm tactics ideas. And so some of the things that have come up as well established in some of the human-swarm interaction literature, the kind of the distinction between what we say neglect tolerance, so our robots, if they don't hear from us, can they handle themselves? How well can they tolerate their supervisor's neglect? But also neglect benevolent systems, those agents that are sufficiently capable that they actually benefit by being left on their own, and only by virtue of human interaction do they need to have major course corrections. And quite frankly, the way we interact with our kind of warfighting units, for example, you try to provide, I think you used the term rules of engagement. You want to provide guardrails, but otherwise really don't micromanage. You defer a lot to the individuals or the subunits within those teams of people. So it's, command by negation is a term that, for example, submarines, when they go get deployed, because you can't communicate them readily, you defer a lot of that decision making to the skipper of the submarine, and only when you have to tell them not to do something do you try to engage. I think that's an interesting model for swarms where, as earlier panelists mentioned, it's really hard to understand what that swarm is doing, and not even clear that you want to measure individual agents in how well they're responding to the swarm tactic or swarm command. So I think there's a really distinct role there to explore, and it kind of circles back to the human-swarm interaction question we've been having.
And so on that topic, so the one thing that comes up typically when you talk to, say, lay people about this is Skynet, right? So essentially, do you want emergent behavior in the swarms that you're designing? Do you folks have thoughts on that? So essentially, do you want the swarm to behave or design it to behave in the way that you expect it to, or would you like it to learn and come up with things that you don't expect, even though that may have negative repercussions?
I think it's a risk reward. I can go back to that statement. If you're willing to let the swarm sort of, become the jazz improviser, then you better be willing to, accept any possible consequences, right? So it's really a context-driven question. One way to answer that question is I'd like to be able to have a range of possibilities. Right? And I'd like to understand what the range of possibilities are, and I'd like to at least know that in a given context, I'm enabling the swarm to do this and not that, or to take it. To me, that would kind of bracket the science questions, and then smart systems designers, like Erin's people, can come along and pick up that toolbox and use it in a way that's going to fit into a particular. So that's kind of how I see it from a research perspective.
Yeah, maybe to follow up on Brian's comment there, I do think that there's a slight distinction. I think emergence, unpredictability, novelty that arises, being able to be surprised, that might be fearful in some contexts, but actually it's quite advantageous in a number of settings, such as trying to go up against an adversary that would love for you to be very predictable and therefore easily countered. Video games would be incredibly boring if you knew when everything was going to happen, right? If everything was scripted. So I think from that perspective, emergence could be a tool that one could really capitalize on and make use of in broader settings. But I think the distinction might be on the employment and the ethics associated with it, which is probably its own icon panel for the future. But understanding what the employment and context, as Brian mentioned, I think is certainly key. I think we could have emergence and still have it be an incredible force for good. And that in and of itself might not be the thing to shy away from. Mm-hmm. Spring, you must see highly unpredictable behaviors and emergence happen, and that's usually something you capitalize on to drive system behavior a particular way.
Yeah, I think at the individual agent level, you can't really predict what each agent will do if they're using these kinds of stochastic control policies, or if the environment is uncertain. So I guess one thing we try to do is develop these macroscopic models that describe the overall behavior of the entire swarm. And in cases where they're an inaccurate model, then you can prove things about the swarm, or at least their average behavior. But of course, there are cases where they're not going to be an accurate model. So then you might, the noise or the low numbers of robots in some state might produce, multiple equilibria or, more unpredictability. So if we can harness that or characterize it in some way, that would be useful as well, at least to see what the performance envelope or possibilities of the collective performance are. So.
Erin, did you have any perspectives on that from the systems side? I think you're muted. Oh, there you go.
Sorry, I was muted. mean, we've certainly experienced some of those emergent properties in the field. I recall a time where we actually swapped out how we were doing our bidding system with one of the sprinters, and so it resulted in just something that we weren't expecting, and the system kind of behaved in a surprising way and loss of comms. So there's been several things like that we've kind of seen emerge that we're at that individual layer. Yes, there's going to be a lot of variability, but we have seen some of that, and honestly, it can be a little scary at first. But very much so. But in terms of, I think it's almost inevitable that that is going to happen as we're mixing and matching different types of platforms and putting them in new settings and then using them in these novel, fleeting ways. I honestly think that the surprise and the emergence is almost certainly going to happen. It's how we control for it. I love the concept of tweaking those knobs. I think that's the great paradigm to think about. And then, of course, that transparency back to the human. But I think it's inevitable.
I think there's an interesting take on this question in that, our military guys are amazingly highly trained, number one. Number two, our system is extremely effective in the field because our guys are enabled to be smart in the field. They don't have to follow literal commands. Instead, they understand commander's intent. They understand how to work together. They're highly trained teams. And where I'm going with this is you put a piece of technology in their hands, they're going to use it in ways that none of us anticipate today. Because they have a need and they're smart and they're like, hey, we can do this with that, right? And so in some sense, our job is to give them that, a rich enough swarm, right? That they can do exactly this kind of playing around, and not be so predictable or adapt the tool to the job at hand. And so.
No, yeah, absolutely. And me coming from human computer interaction perspective, that's why I want access to those users, put them in control of what we have now. Because I think there's going to be so many things that we didn't necessarily think about when designing the system. And I mean, I think what we want to get to is we want to get to the point where the swarm obviously can carry out that commander's intent without the operator having to be left foot, right foot.
Certainly makes certification a challenge, however, I suppose. Guaranteeing surprise and safety is always a challenge. So we're getting to the 4 o'clock hour here. If there's any final last question from the audience, now is the time. Otherwise, this has been a real pleasure, right? So I think these are 5 really top experts in the field here, giving us their perspectives on the challenges and the capabilities. And so for all the students that were in attendance here, I think it's been an inspiring panel and has given them a lot of things to work on. So with that, we will conclude the panel here. I'd like to thank the panelists again, Professor Spring Berman, Dr. Erin Cherry, Dr. Tim Chung, Professor Shaoshuai Mou, and Brian Sadler, Dr. Brian Sadler. Thanks so much.
Thank you.
Take care, everyone.
Thank you.
Thanks, Shreyas.
Thanks, Brian.
Thank you, everyone. Cheers.
Cheers.
Bye.
Bye-bye.
Bye.